Networks and clustering. Often we want to cluster data, which is known as unsupervised learning. In other words, learning an underlying structure. And that usually requires some concept of nearest neighbors. Let's look at the difference between supervised and unsupervised learning. In supervised learning, data has a response or a label. In unsupervised, it has a topology. Our goal in supervised is to predict a response, and unsupervised is to predict properties of that underlying structure. In supervised, we learn a mapping. In unsupervised, we learn a structure. In supervised, we use a function model. In unsupervised, we're trying to get into the data itself. The two are not mutually exclusive. We very often use both. Clustering is unsupervised learning, finding hidden structure in unlabeled data. Now, when we do clustering, what we're really doing is choosing some kind of a means of measuring similarity. Then a cluster has high similarity within the cluster, but low similarity between different clusters. There's a visual illustration. So a data cluster is analogous to a graph component. High similarity within, low similarity between. So this is obviously three clusters of data. And if we use a nearest network model, we have three components. If we have more neighbors, we'll lose the concept of components, but we still have three network clusters. In other words, data clusters are analogous to network clusters. So similarity kernels are used for networks and for clustering, which are analogous. Clustering methods use a similarity kernel to define nearest neighbors, and then use similarity to predict clusters. So suppose we have a similarity kernel, k of xy, then it's 1 if and only if x and y are identical. The closer k of xy is to 1, the more similar x and y are. It's always less than or equal to 1, but no lower bound is required. And it's symmetric. It's also sometimes called affinity, and this comes from the concept of chemical affinity in genomics, proteomics, and chemistry. So we need good models of similarity. We can build more sophisticated models of similarity by using simpler kernels. For example, suppose we have two kernels, K1 and K2. If we take a linear combination in which the coefficients add to 1 and are non-negative, that's called a convex combination, then the convex combination of kernels is a kernel. For example, the average of kernels is a kernel. The product of kernels is a kernel. If we have a distance measure, d of xy, the distance from x to y, then we can define a kernel by taking the exponential of negative beta d of xy to the rth power for beta and r positive. If x is close to y, then the distance is close to 0 and the kernel is close to 1. In other words, distance close to 0 can imply similarity. Here's some common distance measures. We've got x and y as vectors. Then the Euclidean distance is the square root of the sum of the squares of the differences. The Manhattan distance is the sum of the absolute differences. And again, we have distance here because we often replace similarity by, quote, distance close to 0. We often use sigma notation. So for the Manhattan distance, we can rewrite it in sigma notation, as you see here. And the same with Euclidean distance, the square root of the sum j equals 1 to n of the differences squared. Now, when we're working with sigma notation, it's important for you to remember it's just a notation for addition. If you get confused by it, when in doubt, write it out. So this doesn't mean some kind of an operator or anything like that. It just means addition. Write it out as an addition. So we also use norm notation. So the Manhattan distance is called the L1 norm. and the Euclidean distance is defined by what's called the L2 norm. So we'll need high velocity algorithms, and yet finding neighbors is very slow. Nearest neighbor methods are most useful with very large data sets with low noise. But that means that you have to do huge numbers of similarity calculations for a straightforward approach. So high velocity algorithms tend to use distance measures, closeness instead of a general concept of similarity, because distance measures satisfy the triangle inequality. And the triangle inequality allows algorithms that avoid large numbers of calculations by rearranging into what are called tree networks. For example, to find the k nearest neighbors in d dimensions, d is the number of features in each observation. I'm illustrating here with k equals 1 and d equals 2 in the SH plane. We split at the median of the first coordinate, so we split the s's. Then we split the splits at the medians of the second coordinates, in this case the h's. And we continue doing that until we've finished. Afterwards, we can use a binary tree to find a nearest neighbor to a new SH pair. So if S is greater than M1, then notice we don't have to do anything to the left of M1. We don't have to find distances at those points. And then we have a binary tree, which allows us to march down through the boxes until we're done. But there are issues. Now, if D is large, then we get the cursive dimensionality, and that makes KD trees impractical, in addition to some of its other issues. So the ball tree algorithm uses balls, hyperspheres in higher dimensions instead of boxes. But other than that, it's the same idea. You're partitioning the data down to the smallest spheres. Then you do, once again, a binary search. And I want to mention both algorithms are useful. So clustering algorithms that use nearest neighbors tend to be based on distance rather than similarity. And in general, clustering is on distance instead of similarity. So let's look at some of these. We're going to start with k-means, which actually does not use the nearest neighbors concept. So in k-means clustering, you choose k initial points for k clusters as centers of the clusters. And then you repeat until the centers stop moving around, in other words, to get convergence. Label each data point with the closest center, and then replace each center by the means or averages of same labeled data. Let's illustrate. So here we have randomly chosen the 3 x's for 3 clusters, and then we relabel the data based on which of those x's they're closest to. The x's then move as we take averages, and eventually they settle in. Now, agglomerative clustering, or dendrograms, you assume each point is in a cluster, and then you repeat the following until you are done. You link pairs of clusters to create a new cluster. And the linkage is based on a linkage criteria between the sets. So for instance, here we have the data is paired with its, each point's paired with its closest neighbor. And then we agglomerate or link the pairs to each other. And then we link the links of the pairs. And finally, we end up like this. And that allows us to create a clustering. Density-based methods, these are a little more involved, but very useful. So for some epsilon greater than 0, the neighborhood of a data point is a hypersphere with radius epsilon. And a point Q is reachable from P if you can find a sequence of points from P to Q such that each next point is in one of these hyperspheres centered at the previous point, as you can see here. Reachability then defines clusters, and one-element clusters become noise or, quote, spurious. Now, we can also use k nearest neighbors to do clustering directly. This is called spectral clustering. So we start out by creating a k nearest neighbors graph, and then we use eigenvector methods to separate into clusters, or as you see here. Now, clusters are not just bunches. Remember, a cluster is defined by high similarity within, low similarity between. So for instance, we have this data set. If we create a nearest neighbors graph with 5 neighbors each, we end up with this. And then we can choose the 2 components to be the 2 clusters, and we end up with this clustering of the data. Here's a comparison of these methods. It's actually from scikit-learn. Times in the lower right corner. Spectral methods tend to be slow. You'll notice that. You'll also notice that k-means assumes convexity, and this makes it a little limited in application. But clustering often does use similarity. Don't be a slave to fast algorithms. Solve your problem. That's the important thing. Spectral clustering works with any similarity kernel, but it is not fast in general. Here's how it works. You choose a similarity kernel and get a nearest neighbor network representation for your data. You construct a network Laplacian matrix, and then coefficients of eigenvectors of the Laplacian imply clusters. We don't want to get that far into linear algebra, but we'll show you a simple example. First, let's look at some common similarity measures. There's correlation, and there it is in sigma notation. And cosine similarity, if you had the x bars and the y bars equal to 0 in the correlation formula, will give you cosine similarity. Now we can look at this if we define a dot product of 2 vectors to be the traditional sum of the products of the corresponding coefficients. There it is in sigma notation. The cosine kernel is defined to be the dot product over the sum of the squares of the x's and the sum of the squares of the y's. There it is. But this means that x in cosine similarity, x is similar to y in the sense of direction. In other words, the kernel is x dot y over the norm of x and the norm of y, and those are the Euclidean norms. And that actually is how you define the cosine function for the angle between 2 vectors. If k of xy is close to 1, then x and y are approximately parallel, as you can see here. And if the norms are practically the same, then that means x and y are practically the same. So here's my illustrative example. If you look at this very simple data set, you'll notice that observations 0 and 1 are close in the feature space spanned by f0, f1, and f5. But observations 2 and 3 are close in the space f0, f1, and f6. The cosine similarity matrix really just points this out immediately. Now notice that this is a kernel, but there are only finitely many values for x and y. So when you put all these kernels values for all the possible x and y's into a rectangular array, you get a matrix. And for k equals 1 nearest neighbors, it's clear that observations 0 and 1 go together and observations 2 and 3 go together. We get this kind of a graph. The Laplacian matrix is the degree matrix minus the adjacency matrix. Notice that in our k nearest neighbors, this is 1 nearest neighbors, all have degree 1. And this is the Laplacian matrix. You'll notice that if I take the Laplacian times this vector, I get 0 times that vector. In other words, this is what's known as the Fiedler eigenvector of L, and that Fiedler eigenvector of L clusters our data. So unsupervised learning is an effort to predict properties of an underlying structure or topology. Clustering is a form of unsupervised learning. These methods tend to suggest network models, and similarity kernels are used in clustering and network models both, as we've seen, and very often with distance in place of a more general similarity. Networks and topologies are closely related concepts, but there are issues.